we wanted to look at just a fairly simple web path. It has a driven roller. All the blue rollers in this simulation are driven. So we have a driven roller in span 3, we have a nip in span 6, and we have a driven nip in span 11. The other rollers are idler rollers in this simulation. It's a 20-second simulation. We ramp up the speed of all these rollers at different rates and different final speeds. And we can look at the tension as an output. We can look at this amplitude to wavelength ratio, and we can look at the roller misalignment angle that would be needed to generate a trough in each span. Now, to understand sort of the robustness of this particular web path and see how might it do with different types of materials, we have 2 example webs that we want to run this simulation with. The first, which is a higher modulus, a stiffer web, is a polyester film. You could see in the table there, we've got its thickness, its width, its machine direction modulus, its cross machine direction modulus, and a Poisson ratio. And then we have a very different web, a polypropylene nonwoven with much different properties in terms of stiffness, much lower modulus than the polyester film. So let's take a look at the outputs of this simulation for these 2 different webs. But first, again, showing how this is represented in the library. It's fairly basic. You've got an unwind and the rollers connected together with spans. In each span, we put a sensor in there to measure the trough roller misalignment angle. So we created basically a sensor, and we created a custom component to do that trough calculation from misalignment angle. We also calculate the amplitude and the wavelength with another custom calculation, and we'll output that as well. So this is a case for the polyester web. I believe that's the polyester web. And it's just showing the tension transient and the fact that you have different ramp up rates of the different rollers, and you have a little bit of a transient there at the beginning, but it does settle out here by, about 16 seconds. We're basically at steady state. Now, this is the trough amplitude to wavelength ratio for the polyester film. And I said on the earlier slide that if we exceed 0.05 for this ratio, that might be a watchout. For this stiff web, for the tensions that we had input and the roller speeds, it appears that all of these ratios are okay. They're all lower than that limit. So we might not expect, any troughing to occur for this particular web with this particular setup. Now for the polypropylene nonwoven, we can look at the tensions. It's a similar shape to the simulation, but the tensions are much lower. We see that the tension in span 4 is pretty low, but not 0 at steady state. And now if we look at the trough to amplitude ratio for this lower modulus web, though, we see that there are several spans. In fact, most spans are above 0.05, and some are above 0.075, which is a particularly troubling sign that perhaps the tension, if you were to basically just swap out a polypropylene nonwoven web for a polyester web in this web path without making any changes, you're going to run into some problems with over tensioning and troughing, and most likely wrinkles occurring just from having too high a tension. So we can simulate, well, what would we want to do to try to fix this? So we can reduce things like the unwind braking torque, and we can slow down the first driven roller and the exit nip speeds as a case study. And we can see the tensions are even lower, now 2 to 20 newtons versus in the 40 Newton range for the high end. Still above 0 in span 7 on the tension. And now all of these spans are now below that highest 0.075 amplitude to wavelength ratio. There's still some above 0.05, so we still might have more work to do, but we've certainly made it better for that particular web. So let's switch now to the roller misalignment angle. How much misalignment can this web tolerate? And of course, we're not just getting a single value, we're getting the entire 20-second simulation. So you can see if there's a particular part of the ramp that is more or less tolerant of misalignment. And in this case, in general, the misalignment angles are pretty small of what you could tolerate before generating troughs. There's a rule of thumb just found in researching and testing by Oklahoma State that about twice the misalignment angle to generate a trough is what would generate a wrinkle. So you can see that about 1/10 of a degree or tenths of a degree matter for this web with respect to misalignment and generating wrinkles. So for this very stiff web, misalignment is going to be something to really watch out for. For the polypropylene nonwoven, its properties allow for a little bit more misalignment. It's more up around the 1 degree instead of 1/10 of a degree. Although you do see one span sticking out there, span 4, seems to be more sensitive. So that's one of the other benefits of this, is maybe you can see which of your spans are more intolerant to misalignment than others, at least in this simulation. If we go and we look at the case where we lowered the tensions in the polypropylene nonwoven, now we see that you have a few spans getting down, particularly span 7 is now in the 0.2 degree misalignment range. So lowering that tension made at least one span more sensitive to misalignment. And it's all because of different span lengths and different tensions in these different spans. So it's not a singular value. It can change with different conditions, and that's the kind of thing you can explore with this simulation. So to summarize, obviously, I've only touched on a few common issues that can happen with web handling, and there are many just because of the very thin nature of the material, the fact of the speeds that are needed to be run to economically convert webs into products. And so success is going to depend in web handling on how these web and machine interactions are handled. And hopefully I've shown you that the MapleSim's Web Handling Library enables understanding and solving some web handling challenges.